Now let us discuss about the electric field due to an infinite long plane sheet. How will you derive an expression for electric field due to an infinite long plane sheet? For that, let us consider a plane sheet just like this. This plane sheet is extended to both the ends infinitely. This is not a finite sheet but an infinite sheet of infinite length. Let this plane sheet is composed of positive charges uniformly distributed throughout this plane sheet like this. Now before doing anything, first we have to find the direction of electric field around the plane sheet. For that, let us consider a point P, any point P at a certain distance away from the plane sheet. Suppose if I draw a perpendicular from this plane sheet to this point, it will be like this. Now, if I consider a charge here, this charge, this charge will create an electric field in this direction. Clear? The direction of the electric field to the point is along the line joining the charge and the point, and it is for the positive charge, it is away from the charge. Similarly, there will be a equal charge at the same distance from this line, just like this. Suppose these two charges are at the same distance from this white line, because there is always a charge at the same distance from this charge. Clear? And the electric field produced by this charge at the point will be like this. Now, if I resolve the blue or first take the green line, if I resolve this electric field, this green electric field, that is the electric field due to this charge above the line, I can resolve that as one along the horizontal, so one along the vertical and one along the horizontal. Similarly, this blue electric field due to the charge at the downside of this line, I can resolve that one along the vertical and one along the horizontal. And clearly these two electric field, that is this one and this one, are equal and opposite, so they will get cancelled. You know, the electric field due to this charge and this charge is the same because the distance remains the same. So these two will or vertical components will cancel and the horizontal components will add up. So which means the electric field will be only in this direction. And this is true for every point, that is there is always any charges, the pair of charges like this. So the electric field is in this direction, or in the electric field will always be in the horizontal direction. Now back to the derivation. So always remember this point. Okay, let me erase this. Let me again draw the charges. So we have these positive charges uniformly distributed like this, and we found out the direction of the electric field. The electric field will be in the horizontal direction. Now let us consider a circle like this of cross-sectional area A. Let A be a small cross-section, a circular cross-section on the plane sheet. Remember, there will be two sides for this plate, one on the right and one on the back side. See, the plate is like this. So this is the front side and there is a back side also. Always remember that. Now, we need to project a Gaussian surface. Let there be a cylindrical Gaussian surface projected to both the sides. One to the front side and one to the back side, like this. In order to derive the electric field, we always have to consider a Gaussian surface. Let's take a cylindrical Gaussian surface, and the different areas of this cross section are, let me erase this, otherwise it will get confused, the notations 1 and 2. This cylindrical Gaussian surface has three areas. One, the curved surface, the other one, second one, the cross section, and this is the third area. Clear? Now we have the flux through. Before that, let Q be the charge inside the circle. That is inside this circle. Let sigma be the charge density. So you know what is the relationship between charge density and Q? We have charge density equal to Q divided by area, where A is the cross-sectional area, implies Q equal to sigma A. Let's call that as equation number 1. And in order to find the electric flux through this whole Gaussian surface, let's say total electric flux, let's call total electric flux as phi, will be the flux through all the areas, that is flux through this first area, this curved surface area, plus flux through this second curved surface, flux through this cross section area, second area, plus flux through the third area. Clear? So phi will be, electric field is always in this direction. We already proved that. Will be in the horizontal direction. On the other side, it will be in this direction. Clear? So anyway, it is horizontal. So the flux through the first area, that is this curved surface area, will be E dot, let's call that as area. This area will be A1, plus area is a vector. So the second flux through the second surface will be E dot A2, plus the flux is equal to dot product of electric field and area vector. Now along the third surface it will be E dot A3. Clear? Now we have to look at the angle between this electric field and area vector. The electric field, let us consider the first area. The area vector will be in this direction. A1 is in this direction. Clearly, area and electric field are perpendicular to each other. So total flux phi equal to, we can write this as EA1 cos 90, plus for the second area, the direction of area vector will be in this direction, A2. Clearly, the electric field and area are parallel. So we can write as EA2 cos 0. And for the third area also, the area vector will be in this direction, A3. So the angle between electric field and area vector is 0. So EA3 cos 0. Okay, let me erase this. Now simplifying, you will get phi is equal to E. See, I don't have to write this because cos 90 is 0, so this term will be 0. 0 plus, remember we have A2 equal to A3 equal to A. See, these three areas are the same, which is equal to the area of cross section A. We already considered the area of the circle is A. So they all have the same magnitude, which is equal to A. So this will be E, instead of A2 you can write EA cos 0 equal to 1, plus here also it is EA cos 0 equal to 1. So phi is equal to 2EA. Let's call that as equation number 2. Now you can apply the Gauss's law, that is, according to Gauss law, we have phi is equal to 1 by epsilon 0 q. This is according to Gauss law. According to Gauss law, Gauss's law. Let's call that as equation number 3. And if you compare the equation 2 and 3, they both say the same thing. That is the total flux. Now you can equate the equation 2 and 3. That is equation 2 equal to 3 implies we have 2EA is equal to 1 by epsilon 0 q. But from this equation, you know q is equal to sigma A, which means implies 2EA equal to 1 by epsilon 0 sigma A. Clear? Let me erase this. So you can cancel this A. Therefore, E is equal to sigma divided by 2 epsilon 0. So this is the expression for electric field due to an infinite long plane sheet. Remember, the electric field is along the direction away from the sheet and is horizontal or perpendicular to the plane of the sheet. So you can write this as in the vector form E equal to sigma by 2 epsilon 0, let's say some n cap, where n cap is the unit vector perpendicular to the plane or plane sheet away from the sheet. Clear? So this is the vector form electric field. Clearly, if you look at the equation, if you analyze this equation, you will never find a distance term in here. That means electric field at this point, let's say there's a point P in here, let's say there is a point P dash in here. The electric field at both these points remains the same because it is independent of the distance from the sheet. It only depends upon the surface charge density. Now let us discuss about the electric field produced by two parallel plane sheets. Suppose there are two parallel plane sheets like this. Let's call that as sheet number 1, and another plane sheet, sheet number 2. See, this is not a finite sheet, it is of infinite length. For convenience, we just draw this as a plane sheet. Okay, these two are infinite long sheets. Suppose this is positively charged, this also is positively charged. We need to find the electric field produced by these two sheets. So for convenience, let's draw this sheet as a straight line. It also represents this plane sheet, but for convenience, let's draw like this, a line. And this sheet like this. Clear? Clearly, it is like this. But in order to represent that as in one dimension, let's draw like this. Clear? Let me erase this. We have, let's call this as sheet number 1 and let's call this as sheet number 2. Both are infinite long sheet. Let this be charged positive. This also charged positive. Let sigma 1 be the charge density of the first plate and sigma 2 the surface charge density of the sheet 2. Clear? Now let us Draw the electric field produced by these two sheets on different regions. Let us consider the first sheet one. See, the electric field on the right side of the sheet will be in this direction. Clear? On the left of the first sheet, it will be like this. Let's divide this region into three. One, first region on the left of the sheet, region 2 between the sheets, and region 3 on the right side of the sheet 2. So for the sheet 1, the electric field produced on the region 1, see, it is on the left side of the sheet, so it will be in this direction. Let's call that as E1. Now the region 2, second region, is on the right side of the sheet 1, so the electric field, see, it is away from the sheet towards the right, so it will be in this direction, E1. See, this E1 means the electric field produced by the first sheet. And on the third region also, it is on the right side of the sheet, so electric field will be in this direction, so E1. Now let us consider the electric field produced by the second sheet. For the second sheet, on the right side, it will be away from the sheet. On the left side, it also is away from the sheet. So this is the direction of electric field on both sides of the sheet 2. So in the region 1, see, it is away from the sheet 2 and towards the left, E2. And in the region 2, see, it is away and towards the left, E2. On the region 3 is on the right side of the sheet 2, so the electric field is in this direction. Clear? Let me erase these two. Clear? Now we need to find the electric field on the region 1. On the region 1, let's say the net electric field be E1. Clearly it is, see, you can see that both the electric field is towards the left. So the net electric field is minus E1 since it is towards the left plus minus E2. Let's consider only the scalar E1 plus minus E1, E2, since both these electric field are on the left side. So this is equal to, clearly we already derived electric field will be sigma by 2 epsilon 0. So for the first sheet, it is equal to sigma 1, since its charge density is sigma 1 divided by 2 epsilon 0, plus and minus will make it minus. For the electric field due to the second is equal to sigma 2 divided by 2 epsilon 0. So E1 can be written as minus 1 by 2 epsilon 0 sigma 1 plus sigma 2. Clear? If special case, if sigma 1 equal to sigma 2 equal to sigma, since both, let us assume that both these sheets have same charge density, then E1 will be minus 1 by 2 epsilon 0 sigma plus sigma. So this is equal to 2 sigma, you can cancel this 2 and 2, so it will be sigma by epsilon 0 if the charges remains the same. Sorry, charge density remains the same. Now for the region 2, let me erase this. On the region 2, the electric field, net electric field on the second region, see, this one is towards the right and this one is towards the left, so they are opposite direction. So E1 minus E2 is the net electric field. You have E1 equal to sigma 1 by 2 epsilon 0 minus E2 will be sigma 2 divided by 2 epsilon 0. So this is equal to 1 by 2 epsilon 0 sigma 1 minus sigma 2. What if sigma 1 equal to sigma 2 equal to sigma, if both the sheets have same charge density? Clearly, on the second region, it will be 1 by 2 epsilon 0 sigma minus sigma, which is equal to 0. So there is no electric field in between these two sheets if the charge density are the same. Now, for the third region, on the region 3, on the region 3, clearly this is the same case as that of the first region. The net electric field E3 is both directed towards the right. So it will be E1 plus E2. That is equal to sigma 1 by 2 epsilon 0 plus sigma 2 divided by 2 epsilon 0. So E3 will be 1 by 2 epsilon 0 sigma 1 plus sigma 2. Clear? If sigma 1 equal to sigma 2 equal to sigma, then E3 will be 1 by 2 epsilon 0 sigma plus sigma, that is equal to sigma divided by epsilon 0. Clear? So this is the different electric field produced by the different regions of a plane sheet of same charges. Clear? Now what will happen if one is positive and the other is negative? Let's discuss that also. Suppose you have a plane sheet like this and another plane sheet like this. Suppose this is positively charged sheet and this one negatively charged sheet. Let's take this charge density be sigma and that of this one is also sigma. Let us take the magnitude only. They have same charge densities. Now, the electric, let's call this as sheet number 1 and let's call this as sheet number 2. And for the first sheet, that is this one, the electric field on the left side will be in this direction. And on the right side of the first sheet, it will be in this direction. So let's call this as region 1. Let's call this as region 2. Let's call this as region 3. Like we named before. So the electric field on the left side of the sheet 1 will be E1. And for the sheet 1, in the region 2, it will be in this direction. Let's call that as E1. Let's take that as E1. Here also it is E1. Now the electric field for the second sheet. See, this is a negatively charged sheet and the electric field is directed towards the sheet. So on the left side, its electric field is in this direction, that is towards the sheet, and on the right side, it is towards the sheet in this direction. Clear? So the electric field for the sheet 2 in the region 1 will be in this direction, E2, and in the region 2, it is in this direction, E2. E2 represents the electric field of the sheet 2. And on the region 3, it is in this direction, E2. Now we have to find the net electric field on the different regions. Let's see, on the region 1. See, let's take the first region. On the first region, we have the electric field are in opposite direction. So the net electric field is equal to E1 minus E2. So E1 equal to sigma divided by 2 epsilon 0 minus, see, we have considered both sheets having same charge density. So sigma by 2 epsilon 0. So this will be 0. We have electric field is equal to sigma by 2 epsilon 0. We already derived that. Now on the region on the region 2, we have the net electric field E2. See, they both are in same direction. So it is equal to E1 plus E2, that is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. That will give sigma by epsilon 0. And on the region 3, on the region 3, we have the net electric field on the third region. That again is equal and opposite. So E1 minus E2. That is sigma by 2 epsilon 0 minus sigma by 2 epsilon 0. That is equal to 0. So there is only electric field in the second region. Clear?